let's talk about how to calculate the work done against friction. Now, we've done a little bit of this before. So when we're talking about friction, the formula is really about distance, not displacement. We use the average force times the change in position when position matters. But when position doesn't matter, we use average force times distance. So we need to know that friction is one of those cases where position doesn't matter. This is the one we want, average force times distance. So we can begin by looking at the situation of our young man here who is going to drag a chair. We imagine the free body diagram where there is a force applied and a force of friction in that direction. And we know these two are equal and opposite to each other when dragged at constant velocity. And this is important, at constant velocity. We get a little deeper into work, energy, and power. We'll learn why the constant velocity is important. But for now, we want to imagine that this is just being cold at constant velocity. And that is a key component of average force. If we're talking about average force, we mean average force or constant force. So we begin with this free body diagram, knowing this about the forces that are at constant velocity. And we can just remind ourselves of Newton's second law, which tells us the net force is the sum of the forces. The net force is ma, and the forces we have are the applied force and the force of friction. That's what we drew in our free body diagram. And we know the acceleration is 0. Why? Because we said it's constant velocity. So we then have come to the conclusion that the force applied plus the force of gravity add up to 0, and therefore the force applied is equal and opposite to the force of friction. Excuse me, I kept writing force of gravity here and I meant force of friction. So the applied force and the force of friction are equal and opposite to each other when the acceleration is 0, constant velocity. So we use this formula, work equals force times distance. We could use force times displacement if the student dragged it this far. It won't make a difference. We could use F delta X or FD because the distance is what we're concerned about. But now let's imagine the student drags the chair in a circle and returns it to the beginning. Now what we saw is the student dragged the chair, this 4 delta x, 1 delta x, 2 delta x, 3 delta x, 4 delta x, and the position of the chair changed. It is now in a different location, 4 delta x to the right. Now if the student then drags it in a circle, and we say the distance from here to here is delta x, and the distance from here to here is delta x, and the distance from here to here is delta x, and from here to here is delta x. What we can see is the distance from here to here is the same as the distance around the circle. So the distances are the same, but in the case of the circle, the displacement is 0. The position hasn't changed. The final position and the initial position are exactly the same, so there's no change in position. Now we would say the student did work dragging the chair from here to here. And we would say the student did work dragging the chair from here to here. So since the work is done against friction, that work has been done against friction, and we would use F, the average force, times the distance, which would be the same delta x. So if we said the force was 2 newtons, well, we would have 2 newtons, and we would say the delta x, let's say each delta x is 1, so we would have 4. That would give us 8 joules of work was done. And if we use the average force, being the same average force of 2, and the distance now is the same 4, because the distance traveled around here is 4, that gives us a Again, 8 joules. So when we're talking about friction, it doesn't matter if we use, we need to use the distance. It does matter whether we use delta x, because delta x in the second case would give us 0. The position didn't change. And we would all agree that the student dragging the chair around the circle did do work against friction. Now, the last element that we want to talk about here is what happened to the energy that was expended. You know, we might agree that the student ate some food and they have energy in their bodies and they exerted energy to do this work against friction. Well, ultimately what happened was we had food being converted to energy of the person, which did work against friction. And where did that go? Well, that went into thermal energy. We know that friction tends to heat things up. So all of the work that was done moving this chair around went into heating up the bottoms of the chair legs and the ground that it was dragged across. So this 8 joules of work that was done went into warming up the ground and the chair legs, 8 joules worth. This idea of what happened to the energy and what did the work accomplish is an important one over the next few days and cases in our explorations into work, energy, and power. What happens to the energy? What happens to the work? In the case of friction, it's always into thermal energy of the two bodies touching each other.